So simple harmonic motion, what we've seen so far is that oscillating objects have this nice cosine or harmonic function there. And that's mainly because the restoring force is always trying to get it back to that equilibrium point, and that's that direction of the force there. What we found also is that if you compare the acceleration with the displacement, then the acceleration graph is actually the complete opposite. Over here, there's actually a really high amount of negative acceleration. At this point here, it's going at constant speed. At this point here, it's actually turning around and going back positive again, so you've got very high positive acceleration. And by the time you plot that all through, you end up with a graph that is the complete opposite of what you had there. So we're going to use those two ideas and see if we can come up with a bit of some equations to go around that. So going back to the displacement graph here, the axes here are quite straightforward. That you've got, that's the up and down, so that's y displacement from our 0 point, our equilibrium, and going up as high as positive amplitude and coming down as far as negative amplitude. This axis, of course, is time measured in seconds, and you've got the thing doing a complete cycle every periodic time, so where you can measure the frequency of something, t is 1 divided by f. We're going to try and get a mathematical equation for that graph, but it presents a few problems. First problem is that the axis here is not an angle. The axis here is in time in seconds. Normally when you plot a sine or a cosine graph, that's going to be an angle in radians that you're plotting against there. And the sine or cosine would always go up to plus or minus 1 as a value. So first, let's just take account of the scaling that we've got because of the amplitude. We can say that y is equal to a cos of something. And it's the something which is the issue, because we can't put seconds in there because cos only returns a value based on a radian measure. So we need to put in something here where 1 full periodic time is actually equal to 2 pi radians. So can we come up with a function in there that does that? We do that by saying if 2 pi is equal to t, then any proportion of that is the variable time along here. So we actually put in a cos 2 pi t divided by t, and so what we're saying is that the variable time here is actually a fraction of the full time here, and if the time is double the periodic time, this would return 4 pi. So it's a scaling factor there, and that now the time in seconds cancels with the period in seconds, so you're now left with an angle, radian angle measure, which is great. So there's various other things that are used here. We also could replace t by 1 over frequency, so you could have y equals a cos 2 pi ft, because instead of dividing by time we're multiplying by frequency. That is a bit cumbersome, so there's a shorthand. We replace 2 pi times f by the symbol omega, and that omega is the pulsatance, which is got the same dimensions as frequency. It's still per second, but because we're talking about radians of angle, then it's actually radians per second are the units for that. So we can rewrite that as y equals a cos omega t, and that is the basic form of simple harmonic motion in terms of an equation. Now this works obviously if you're starting from time equals 0 with full amplitude using cos. You could also have the same thing where you're starting from time 0 with 0 amplitude, and that would be y equals a sine omega t. Both are forms of simple harmonic motion, you could be using either. So we've got a harmonic function, y equals a cos of omega t. That's the amplitude, that's negative amplitude there, and that's time running along. So I'm going to see if we can work out what the equations are for velocity and acceleration time using a bit of calculus. So velocity is going to be dy by dt. Now when you're differentiating cos, remember you multiply by whatever's inside the brackets and change it to minus sign. So you end up with equals minus a omega sine omega t. And that's the... So you can see what we've got here is actually the negative of a sine curve, and that's come from what we had earlier. That's often referred to as y dot in Newtonian notation. Next stage is to get the acceleration. So again, we're differentiating sine, which means you multiply whatever's inside the variable. So we're going to have acceleration is minus omega squared now times amplitude, and this time cos omega t, because the sine converts to a cos in differentiation, and all we're doing now is multiplying by omega again. I've written it this way around because you can see we've got minus omega squared and then a cos omega t. A cos omega t, going back up the top here, is just the y displacement. So we've actually got acceleration is equal to minus omega squared y displacement. So this is saying that the acceleration is always negative the y displacement, and it's proportional to the y displacement. In terms of how that all pulls together for simple harmonic motion, when we come to damped motion we'll find these two here, so we'll come back to those. But you've got this pulsatance is omega, which is equal to 2 pi f. That's measured in radians per second. That the period is 1 over s, which is also 2 pi over omega. And because the equation for speed is a omega sine omega t, we had it negative there before, then the maximum value that can possibly have is a omega, because sine, the maximum value for that is 1. So the maximum speed as a mass, and that's as it passes the equilibrium, is a omega. If you remember, acceleration was minus a omega squared cos of omega t, what we had before. So in that case, if cos is a maximum of 1, then the maximum value that the acceleration can be is a omega squared, which is that value down there. So the equations that you're given by the SQA, remember that the acceleration is d2y by dt squared, so that's the calculus form of it, and that's equal to minus omega squared y, where omega is 2 pi f in radians per second. You're given y equals a cos omega t here, or y equals a sine omega t, and it depends on the initial starting conditions. You may have to choose whether you use cos or sine by looking at, does it start from full amplitude or does it start from 0 amplitude at t equals 0.